Hey guys, welcome back to chapter 14. What we're going to do now is we are going to apply this integrated rate law to a very fun and unique topic, if you will. So what we're going to talk about now is something called half-life reactions. So for a half-life reaction, half-life is defined as the amount of time required for the concentration of a reactant to fall to 1/2 of its value. Okay. So common misconception here: it's not that two halves make a whole. So if I look at this graph, down here on the bottom, we've got time from 0 to 300 going left to right. And from bottom to top, we've got the concentration of a particular reactant. Okay. So after one half-life goes by, so it looks like the half-life for this particular compound is 100 seconds. So after that one half-life goes by, the concentration of this particular reactant goes from 1 molar to 0.5 molar. So the time it takes for the concentration to fall by 1/2. So it went from 1 molar to 0.5 molar. Okay. Another half-life goes by. So another 100 seconds goes by. And it's not that this drops to 0. What happens now is that half of what was left will disappear. So we've got 0.5 molar. Another half-life goes by. That's going to get cut in half. Now we've got 0.25 molar. Okay. So another half-life goes by, another 100 seconds goes by, and now that 0.25 is going to get cut in half. And so now after another 100 seconds, we would have 0.125 molar. So after each half-life takes place, whatever was there at the beginning, half of it is gone or half of it is left. Then we cut it in half again, and we cut it in half again, so on and so forth. Okay. The reason that we are only going to look at first order reactions is that for first order reactions, the initial concentration is independent of the half-life. So for a first order reaction, the half-life is constant and independent of concentration. That's different from a zero order or a second order reaction. So for a zero order and second order, as the concentration goes down, the half-life changes. So maybe the half-life's 100 seconds, then 75 seconds, then 50 seconds. So the half-life changes as the concentration changes. That just sounds messy, and it is messy. So that's why we're going to focus our attention on first order reactions and save the second and zero order for higher level chemistry courses. Okay. So constant half-life, that's unique to a first order reaction. So what I'm going to do now is pretty easily derive an equation for you. So up until this point, I've kind of given you equations and said, here's your equation. Don't ever take my word for it. You guys should always go back and look at where that equation came from. Today, I can pretty easily give you a derivation or show you how I get to the equation that I'm about to show you. You are not responsible for deriving this equation yourself, but I think it gives you a better, more complete understanding of the equation. Okay? So here is our integrated rate law for a first order reaction. So the first thing I'm going to do to this integrated rate law is I'm just going to rearrange it. So what I'm trying to do is I'm trying to get a formula that I can use for half-lives. So the first thing I'm going to do is I'm going to rearrange this. Eventually, I want to solve for this variable right here. I want to solve for t. So it might be nice to know the half-life of something. So that's what we're going to solve for. So the first thing I'm going to do is just rearrange this. So the first thing I'm going to do is just move this natural log of A over to the other side. So to do that, I'm going to subtract natural log of A at time 0. Whatever I do to the right side, I also have to do to the left side. Okay. So we've got natural log of A at time t minus natural log of a at time 0, and that equals negative kt. Okay. So this is one of those fun algebra concepts. So if you have natural log of a minus natural log of a, algebra tells me that I can rearrange this and make it look like this. So natural log of a at time t over natural log of a at time 0. Okay, so that's literally just rearranging this portion. These two things mean the same thing. They're equal the same thing. Okay, and this is just kt. I haven't done anything over there. Okay, so half-life. Half-life tells me that when one half-life goes by, the concentration is cut in half. So I could plug some numbers into this equation here. So let's say at time 0, my concentration is 2 molar. And one half-life goes by. So how much time goes by? A half-life. One half-life goes by, and now what's the concentration? The concentration was 2 molar. It gets cut in half. It's 1 molar. Okay, and you could do this with anything. I could put 4 and 2. I could put 6 and 3. You could do any numbers you wanted to there. Okay. Well, with actual numbers in my equation, now I can plug this into the calculator. So I'm going to take natural log of 1 divided by 2. And that spits out a very helpful number. The number it spits out is negative 0.693, and that equals negative kt. And we've established that this is a half-life, that t is whatever a half-life might be. Okay. So now I'm just going to do one last algebraic rearrangement. So I want to solve for this half-life, so I can say, okay, the half-life of this particular compound is 3 days, okay? So to solve for t, I'm going to move k to the other side. So divide by negative k, divide by negative k, that cancels. So over here, we're left with t, and that's 1/2. And then these negative signs cancel out. So negative on top, negative on bottom. And so we get an equation that looks like this. 0.693 over k will give us the half-life. Okay. Very useful little equation here. So that's how I derived the equation. That's where this equation comes from. So a pretty easy derivation to get from point A to point B that you guys can understand. So I went ahead and took the time to do that. But now we can say for a first order reaction, we can solve for the half-life if we know K. So plug K in and we spit out the half-life. So pretty nice little handy formula there. So let's take a look at some problems that we could ask, some things that we could do. So N2 decays from 0.085 molar to 0.023 molar in 113 seconds. If I have established that this is in fact a first order reaction, so knowing that it's a first order reaction, that just gives us the group of formulas that we can use. I want to know what is the rate constant K for this reaction and what is the half-life for this reaction. Okay. So knowing that it's a first order reaction, we've got two equations that tell us a lot of this information. Okay. So first I want to solve for the rate constant K. So I'm going to use this equation first. I'm going to use the integrated rate law. I'm going to solve for K. Once I know what the rate constant is, then I can use this handy little equation over here. I plug in my value for K, and boom, it's going to spit out my half-life. So that's the path that we're going to take through this problem. So let's work it together. All right. So first things first, we're going to do this reaction. We're going to solve for K. So we've got the natural log. So N2 is the concentration that we're monitoring. It decays from 0.085 to 0.023. So here we're doing the concentration after a given amount of time has gone away. So that's going to be the 0.023. So after 113 seconds, that's what the concentration is. This is going to equal negative K. So we're solving for K. We don't know that. And our time that went by is 113 seconds. And then we're going to add the natural log of the original concentration, which was 0.085. So plug and chug, pretty straightforward algebra problem. So let's clean this up a little bit first. So the first thing I'm going to do is put the natural log of 0.023 into my calculator, and it tells me that this number is negative 3.77. That's going to equal negative K times 113 seconds. And then I plug in natural log of 0.085, and it tells me that that number is negative 2.47. Okay. Careful here with these negative values. You could do a plus a negative. You could just change this to a subtraction sign. But just be very mindful because losing a negative sign can affect the numbers greatly. And they're pretty easy to lose. That's the biggest mistake that I see. Okay. So now I want to get K by itself. So the first thing I'm going to do is move this number, the 2.47 over. So I'm going to add 2.47 to both sides. So that cancels, plus 2.47. So now on the left-hand side, I have K times 113 seconds. And I take negative 3.77 plus 2.47, and this is negative 1.3. Okay. And now to get K by itself, I divide by 113 seconds. I divide by 113 seconds. Here we see our units are, this number is unit list, so seconds on the bottom. So our units are 1 over seconds, which is what we would expect. And I'm going to take negative 1.3 divided by 113, and that gives me negative 0.012. And we still have negative K over here, right? So that negative followed us all the way through. Well, a negative and a negative cancel each other out, so this is just positive numbers. Okay. So what is the K for this reaction? Well, K is 0.0121 over seconds. Okay. What else did it ask us to do? So the first step was determine or solve for K. The second step was determine what is the half-life of this reaction. So now that we have a value for K, the half-life is pretty easy to calculate. So now we're going to take this formula. So we just take 0.693 divided by our value for K, which is 0.012, and that's going to give us our half-life. So we've got 1 over seconds on the bottom. Again, crazy algebra. That tells me that the unit here is going to be in seconds. And then I take 0.693 divided by 0.012. And the half-life for this is 57.8 seconds. So that is a few different pieces that I could ask you about. for these first order reactions and including half-life of the reactions. I would expect you guys at this point to practice. So there's all different ways that I could come at these integrated rate law questions and different things I could ask you to solve for. So at this point, I like to just kind of summarize the chapter because we're going to move forward into something a little bit different. So summarizing just the basics of kinetics, we looked at the rate law. So the rate law relates the rate of a reaction and the concentration of the reactants. So again, if you want to look at concentration and the rate of decay, then you would use the rate law. If you wanted to look at concentration and time, so how long is it going to be around, that's when we would use the integrated rate law. So here's the 3 integrated rate laws that we know. So 0 order, first order, second order. Okay. Reaction order and the rate law must be determined experimentally. So whether you do what we did in lab, and you do something like this and solve for Y, or you take the data and you go to Excel and you graph it, it doesn't matter, but either way, you have to get the experimental data and then crunch the numbers from there to determine the order. Okay. I hope you guys found this helpful. We are going to move on to temperature dependence and then structure orientation dependence now. So that ends the math heavy portion of this chapter.